Everybody, and thank you, Yamila, for coming. So Yamila is an assistant professor at the Leiden Observatory and the Netherlands Institute for Space Research. She studies planetary atmospheres, interior information, and she focuses both on exoplanets and solar system planets towards a better understanding of their origins. She was recognized many times for her work, most recently by winning a European Research Council Consolidator grant. And today she will talk about exoplanet characterization and evolution through synergies between JWST and solar system science. Yamila, thank you so much for coming again, and the Zoom floor is all yours.
Thank you. Okay. So we tested this. Hopefully you are all seeing my screen. Let me just get make all the floating control disappear. Okay. So hello, everyone. Thank you for the invitation. It's really a pleasure for me to give this talk via Zoom. So I will be talking today about the work that I'm doing, particularly on giant exoplanets, and I will say a little bit about solar system as well. But I also wanted to mention the other work that we do in my team. So we are focusing. So here you see some pictures of us. The one in the top are my PhD students. When one of them was graduated, that actually graduated 2 months ago. And then the other photo is also with the extended group with some of the master students as well. So what we do is to work on giant exoplanets, but also rocky exoplanets. Today, as I said, I will be focusing more on the giant ones, but I'm also happy to chat more about the work I'm doing with the rocky exoplanets if you are interested. So let me start the talk right away, and I will divide this talk in 2 parts. So the first part would be about interior of exoplanets, and the second one will be about atmospheres. So really what I want to do is to try to understand how is that one affect the other. So which are the effects of interiors on atmospheres and vice versa, and to see if this is actually relevant for all the great observations we are getting with JWST. So that is more or less how the talk is going to go. So first, let me start talking about interiors. And for these are really the main big questions that I would like to know. And one is, which is the bulk composition, the bulk metallicity of exoplanets, and how are those metals distributed in the interior? And the reason why I think it's important to know this is because giant planets are really the first planets that are born in a planetary system. So they are born when there is still gas in that nebula that gave birth to the entire solar system. And for that reason, they have very valuable information in their interiors and their atmospheres to understand the process of planet formation. It's more difficult to extract this information with rocky planets because they take way longer to be formed. They suffer a lot from giant impacts that really can affect their dynamics and their composition. And they also have some geological processes that change their interiors with time. While on the other hand, the giant planets, they of course evolve with time, and I will be talking about that. But the evolution is in a way way less dramatic than what we see with rocky planets. And that's why we really can observe them today and learn a lot about the formation of these planets. So that is one of the reasons why I want to know more about these planets and why I think it's important to learn about their interiors and their atmospheres. Now, one of the things that I always want to do is to put together the information that we have from solar system and exoplanets, because they are all planets in a sense, and we do know we have different kind of data. So for the planets in the solar system, we have very detailed information. We can go there. We can even measure things in situ and even get samples. So it's really detailed, the information that we can get from the planets in the solar system. But on the other hand, we only have these very detailed data for a few objects. While if we look at exoplanets, we don't have maybe such detailed information, but we do have a lot of it. And that gives us statistics and really help us to, to put the puzzle together. So I think it's really important if we want to understand how planets work and how they form and they evolve to actually look at the entire picture. And that's really why I work with solar system planets and also with exoplanets. So some things about solar system is that it was really a great time to study the giant planets the last past years, particularly because there were two amazing missions that went to Saturn and Jupiter, and those are Cassini and the Juno mission. And both of them were really amazing missions that gave us huge amount of information, very, very detailed information on our gas giants. And particularly, I was involved in the Juno mission, so I'm part of the science team. And I've been working with them since it arrived to Jupiter in 2016. So I really saw all the great things that we learned about Jupiter and how it really changed our view on giant planets' interiors and atmospheres, thanks to all that great data. So let me mention just one of the highlights that is actually relevant for the rest of the talk, but there were really a lot of different highlights that came with this mission, not only about interiors, that is mostly what I will be talking about, but also about the atmosphere, the magnetic field, the differential rotation, the auroras, and so on. So about the interiors, it really helped us to understand the interior of Jupiter way, way better. And that is because, of course, when we had a probe around the planet that was passing so close to the planet, because the orbit of Juno was passing at the closest point, it was 4,000 kilometers above the clouds. So really, really close to the planet. And it also had an orbit that allowed us to pass through the poles. And this change also in the orientation of the spacecraft helped us to get really good gravity data. And that's why we really could learn a lot about the interior. So what I'm showing here is a schematic picture really of the interior of Jupiter, but many of these things we actually learn because of the Juno mission. So what you are seeing here is, so you see some dashed lines. I'm not sure if you can see my, my cursor when I'm pointing. I hope you can, but I will mention anyway things. So the dashed line, the gray dashed line, is actually showing the extent of the differential rotation inside the planet. So all those nice bands that we see in the atmosphere of Jupiter, they rotate in different directions, at different velocities. And this differential rotation of the planet extends not so deep, approximately 4% of the radius of the planet. And this is one of the things that we learned thanks to the gravity data. We didn't know this before. Now, when we go more towards the interior, the planet actually rotates as a rigid body. And that is what we believe and explains the data. And it has different layers. So you see here in the outside a layer that is light orange, and that is dominated by molecular hydrogen and helium. When we go more towards the interior, you see that there are some droplets there. And there are two different things that happen in this layer. First of all, hydrogen and helium separate from each other. At certain pressure and temperature in the interior of the planet, there is what we call an immiscibility region, where basically these two elements just don't want to be together anymore and they separate, like water and oil is a good example. So then there is this separation in different layers. And this thing was theorized in the 70s. So Dave Stevenson was one of the first person thinking about this. But we really didn't know if this was the case or not until the 90s, when we had the Galileo probe that entered into the atmosphere of Jupiter and made in situ measurements. Particularly important were the measurements of the noble gases that actually told us that helium was indeed depleted in the atmosphere of Jupiter. And then this depletion is due to this, or we believe is due to this immiscibility, where helium forms droplets. And these droplets, because they are heavy, they rain down. So this depletes the atmosphere of helium, and we have an overabundance in the interior. Another thing that happens is that hydrogen also has a phase transition and is not in a molecular state anymore. But when we go deeper into the planet, it's a metallic fluid. So it's also very conductive. And we think that is also the region where most of the magnetic field is generated. Now, if we go even deeper in the interior of the planet, we have at the very, very center what we call an inner compact core. And that would be a part of the planet that is very tiny and is made of 100% heavy elements. But then we have another layer that is what we call the dilute core, where these 100% heavy elements mix or dilute into the hydrogen and helium envelope. So this dilute core was actually a new concept that we found with the Juno mission, because it was the only way to really explain the data. And it kind of made really a paradigm change in the interiors of giant planets, because it's a very different thing having just a core made of heavy elements and having a core that is also mixed with the hydrogen and helium, because this creates a compositional gradient in the interior that changes the way that the energy is transported, changes the way that we can explain the formation of giant planets. So it was really an important discovery. So what you can see here are simulations that I made in a paper last year, but also this dilute core is actually was presented for the first time in a paper by Sean Wall in 2017. But you see the amount, the mass of metals in the different regions in the interior of the planet. And it's important to know that there are, of course, degeneracies. So it's very, very difficult to get information from the very center of the planet, because the gravity data is more susceptible to the outer layers. So, we do have some information, because basically we discard what can happen with the rest of the planet, but it's not that this gravity data tells us exactly the mass in the core of the planet. So you can see here that there are different possibilities. One could be that there is no central inner core at all, and all the core is actually diluted within the envelope. Another one is that we have this core and then the rest is diluted. But in all cases, we can put an upper limit to the central core of Jupiter of around 7 Earth masses, which is very small compared to the previous paradigm that was even double or more mass. Now, this is the part that I wanted to mention about the solar system. And now I will tell you why this is important for exoplanets. And the thing is that this is not the only motivation really to think that giant planets are inhomogeneous in their interiors. We have, as I said, the distribution of metals in Jupiter that is showing us really that the metals that we observe in the atmosphere do not really represent the entire metallicity in the envelope. But we are also observing this in Saturn. So we have data from the Cassini that shows also allows us to make these kind of studies using the gravity field. But also for Saturn, we have oscillations. So giant planets oscillate in a similar way as the stars do, but we are not completely sure of what is causing these oscillations. And we can see in the case of Saturn, we can see these oscillations, how they are in the rings of the planet. So then we can do seismology of Saturn using the information that we get from these waves on the rings. And this information is also telling us that the interior of Saturn is inhomogeneous in the same way as Jupiter. So probably that there is this gradient of metals going from the interior to the outer side of the planet. There were also some recent papers doing this on giant planet formation scenarios that also are finding naturally these inhomogeneous interiors. So there is really a paradigm shift in the way that we are thinking on the formation on the interiors of giant planets. Now, on the other side of the story, we now have JWST. That is, of course, amazing. And I'm pretty sure you all know how amazing it is. And the good thing about it is that we have really a great accuracy now that will allow us to see tiny effects in the atmospheres that we just didn't bother to study before because we just didn't have this great data. But now any small effect, we can see it in the spectrum. So really my question is it true that we can see some small differences in the interiors of the planets in this spectrum? And when can we learn about the interiors of the planets with the atmospheric data that we are getting? So this was really the motivation for this work that we did, trying to retrieve, in a sense, interior properties of the planets using atmospheric data. So for this, of course, we need to have a model, and we tried two different ones. So what we call a homogeneous model, that is really the current exoplanet model that we were all using until now, where we have that an exoplanet is made by a core made of 100% heavy elements and an envelope. And the envelope, and you see the dark orange is actually the atmosphere, which is a tiny, tiny, tiny part of the planet. And the important thing is that in this model, the atmospheric metallicity that we were observing was the same metallicity as in the rest of the envelope, because basically we assumed that the entire planet was convective and well mixed. So if we were observing some metallicity in the atmosphere, this will be representative of the entire planet. Now, I was trying to convince you up to this point that this is probably not how giant planets work. So then we need to start thinking about modeling these giant interiors differently. And what we did particularly in this work was to think on also having this gradient of metals in the interior of a giant exoplanet. And in that case, the bad news, in a sense, is that the atmospheric metallicity that we observe does not represent the metallicity in the entire envelope. So of course, this makes things more complicated to try to interpret the results of the atmosphere in terms of the formation of the planet, because we cannot say directly, oh, this is the metallicity that it had, the bulk metallicity of the planet. We need to work that out a little bit more. But I think that this is really the evidence that we are having and the way that we should move in the field. So what we did was to model these interiors of planets. And of course, we wanted to do a retrieval. So we did this with an MCMC approach. And basically what we did was to use an interior model that was based on the one that we were using for solar system planets. So I took the same model that we use for Jupiter and put way less prior data, because of course we don't have that amazing gravity data and other information that we have for Jupiter. We don't have that for exoplanets. So I changed, of course, that, and then to try to calculate different outputs to see what we could learn from these planets. So the observational constraints that we used were the mass of the planet, the radius, the atmospheric metallicity. And for this, we mostly use the water abundance. So when I say atmospheric metallicity, it's really the water mixing ratios. But in the future, I want to really try to do that better also, not only to use water, but maybe if we have for some planets more than one molecule observed, this can help us to pinpoint the real metallicity in the atmosphere. We also use the temperature of the planet and the helium abundance. And for this is really something important, but it's also very difficult, right? Because we cannot really measure the helium abundance. So we use really the protosolar or the protostellar abundances of some of the planets. There are some models of people working with the stars that calculate these things, but it's definitely one of the uncertainties in the calculations. And then what we got as outputs was the mass of metals in the envelope, the mass of metals in this dilute core region, the core mass, and the bulk metallicity of the planet. Okay, so let me show you some of the results. What we did first was to do this with a test planet, because we wanted to know if the method was working or not. And for this, we created an exoplanet that we knew exactly which was the mass in the core, in the dilute core, in the rest of the envelope. And we tried to retrieve those parameters. So when we only use as prior data the radius and the mass of the planet, and we try to retrieve the core mass, then you can see here the results, and it's basically that we cannot retrieve the core mass at all. So here, the dashed line is showing where is the real core mass that we put in our test planet, so the right answer, let's say. And the different colors are showing the results of our retrievals using a homogeneous and an inhomogeneous model, so we tried with both. But we see that you see that there is no way to say which is the core mass of the planet with only that data. And that was really why all the models up to this point were assuming homogeneous planets, because basically we just didn't have good data to know more. But when we add other information, like the equilibrium temperature, the atmospheric metallicity, then you see that our results get way, way better. And this is not really rocket science, is that if we have more information, we can, of course, get more information for our variables, right? If we have more variables than data, there is no way that we can retrieve something. So, of course, if you add more information to your problem, you will be able to extract more about the interior as well, which is very important, because I think that we can say really that atmospheric data helps to constrain the interior structure of exoplanets. And this is really encouraging for the future work. Now, let me show you what we are finding. So once we made sure that it was working, we used this on real exoplanets, and we did it for 39 real exoplanets. And we did this pre-JWST. So the paper came published at the beginning of this year, but we really submitted it, last year when we didn't even have data of JWST yet. So we use as metallicity the data that we had, that of course had huge error bars. We are now working on a second paper trying to include the better constraints that we have. But that's also why you see that the error bars of the data that we are getting is really big, because the constraints that we were using were big as well. So what we are showing here is the mass of metals in the envelope of the planet and the mass of the core. And again, we did this for the two models, for the homogeneous and inhomogeneous. And you see that the answer is not the same. So really, we need to work more on these two models. I mean, it's expected, right? Because they are different models. The error bars are also quite big. So we are now trying to see if with the new constraints that we are getting, we can make these ones smaller. But it's actually very encouraging to have data to be able to retrieve core masses of exoplanets for the first time. And you can see also here the distribution of metals in the interior. And basically this slope that you see is this dilute core region where the metals, where we have this gradient of metals from the interior towards the outer parts of the planet. Now we also, of course, want to know which is the mass metallicity relation. And there were other papers that work with this in the past. So I'm citing some of them here. And the difference, in a sense, in our work is that we are retrieving these using what we call these static models. So we are not really evolving the planet with time. We are just observing the planet right now. We know which are the atmospheric parameters. We know which are the mass and the radius, and then we can try to understand how is the planet today. So this is really a different model than the one that was done before. And the interesting part is that we are also getting similar results. So for some of the planets in our sample, we're actually the same planets that Daniel Torgrim and Jonathan Forney were working with, and we are finding similar answers for the total mass of metals. So I think that is also encouraging, that with different methods, we are getting somehow similar answers. But we are also getting smaller masses of metals than the ones that they were getting. So we also need to work a little bit more to understand those differences in the models. You see here, I didn't mention, but the red ones are Jupiter and Saturn. So really the exoplanets kind of lie in this slope that we observe for the solar system as well. One thing is that we see that some planets have a total mass, let's say, for example, this one that now I don't remember which one it is, but they have a total mass in the sense similar than Saturn, but the metallicity is way higher. And then we try to understand why was that the case. I'm not sure that we understand it yet, but something that we checked was also the metallicity of the stars. And we see that at least these two that have very high metallicities, the stars also have very high metallicity. So I know that there was some people trying to also understand this in the past, and they didn't find a correlation. But maybe now that we have better data, we have to double check and see if there is or there isn't a correlation between the metallicity of the star and the metallicity expected for the giant planets as well. So it will be good to study more that. All right, so let me go with the take-home messages of this part, and then I will move to the atmospheric part of the talk. So I didn't mention, so this work was done by Sane. Sane was actually was a master student, an amazing master student that I had. She's now doing a PhD, but more on radio astronomy and exoplanets in Groningen. And these are really the two, I think, key messages that we found. One is that we can start thinking on doing retrievals of interiors of exoplanets, which I think is really cool. And of course, now with JWST and that great metallicities that we are getting, this will help us to understand interiors of planets as well. Now let me move to the exoplanet part and how all of this is also embedded in the information that we can get for atmospheres of planets. And for this, what I want to know, because this whole talk is more going into understanding metallicities of planets. And then what I want to know is which are the atmospheric metallicities of planets? How do they evolve with time? Because we are observing exoplanets today, right? But maybe they are, very old. And we don't know very well how these metallicities evolve with time. If the ones that we are observing today were the same bulk metallicities that the planets had at the beginning when they were formed. So I think if we want to try to understand the formation of planets and which information the spectra is giving us about the formation, then we also need to understand what happens in the evolution of the planets and how things like metallicities and abundances, how do they evolve with time? So, and another thing is how this changes the spectral features that we are observing. So a planet today won't have the same spectrum as a planet that has, a billion years old. And different ages also imply different evolution of these metallicities and also will give us different features that we can observe. So I think this is also interesting from the observational point of view. So you know that we observe exoplanets observing their atmospheres with transient spectroscopy and emission as well, and phase curves. And for this, of course, we use the JWST these days with all these different instruments. We also use telescopes like the Hubble and Spitzer in the past. And actually the data that I showed before was using that information from Hubble and from Spitzer. So now things are going to move way forward with the new technology. In particular, I will talk about WST-39b, and this is because it's one of the planets that we know the best. Thanks to the early science team for transiting exoplanets, we have information of this planet in all the instruments in JWST, and I think that is really great to use it as a test planet as well to understand other processes. So in case you don't know, so WST-39b is a Saturn mass planet. It has an equilibrium temperature of around 1000 Kelvin. It orbits a normal G7 type star. And it is located as a semi-major axis of 0.05 AU approximately. Here are some of the examples that were obtained by the early science team, which are really amazing. So you see here from different papers, in total, there were 7 papers published with the data from the different instruments. And here you see some examples. So really, we could find CO2 in the atmospheres, sodium, water, CO, very importantly, the SiO2 that we were not really expecting. And as I mentioned before, all the information I'm showing here, some of them, but all of this was published in a special edition where the 7 papers are. One particular result that I think is interesting in the context of studying metallicities is the one by the paper by Shamit Tsai et al. That basically is explaining this bump here, this SiO2 feature that actually was found to be a result of photochemistry in the atmosphere of WST-39b. So it's really the very first evidence of photochemistry in an exoplanet atmosphere. And the reason why I'm putting it here, besides it's a pretty cool result and we should highlight it, is also because SO2 proved to be a very good indicator of metallicity in exoplanet atmospheres, as you can also see in this figure. So So in this figure, the different colors are models made with different metallicities, and you see how the metallicity is really sensitive. So the SO2 feature is really sensitive to the metallicity. So it's also interesting because I showed you that the results before we used as a proxy of metallicity the water abundance, but maybe in the future we can use other molecules that will tell us better how is the metallicity in these planets. Now the question is, how did WST39b obtain this metallicity? And this is a study that we've been doing with one of my students, Amy Luca. She was really doing this study for a general grid of planets. And then at some point she was like, you know, we can just do this for WST39b as a curiosity to see what happens. And this is how this was born. So these are preliminary results. The paper is not published yet. So just for you to know. So basically there are two ways that the planet can obtain the metallicity that we observe today. One of them is through the formation itself. So maybe the planets just form metal rich. And there are some papers about this that I posted there. The other possibility is that the planets are actually born with the same metallicity as the parent star, because basically they are born from the same disk, the same gas. And then they evolve with time, losing the hydrogen and helium and enriching the planet in metals. So those are really the two possibilities. We wanted to see and study a little bit more the second one, to actually see if it was possible or not that the planet obtained the metallicity today just because of the evolution and the atmospheric escape. So for this, this is more or less the scheme that we are using. So we are using a thermal evolution model for the planets. That is actually, we are using the MESA code that is also used for interiors of stars. So we evolved the planet with time using this code, but we are also taking into account the atmospheric escape that the planet is suffering with time. And then we are combining at certain times, we are combining this with the radiative transfer and chemical kinetics code to see which are what's happening in that atmosphere, which is a temperature structure, how is it changing with time, how does that change the chemistry, and how does that change the spectral features? Because we also wanted to see the change in the spectral features with time, if there was any. So, so let me show you some of the results that we are finding. And basically the main result that we are finding, and here what I'm showing is the enhancement, so how the metallicity increases with time as a function of time. And you see that is not that it changes a lot. So in this simulation, we assumed that at the beginning of its life, WST39b had the same metallicity as the star. And then you see that the planet evolved with time, the metallicity increased with time because there is this escaping hydrogen. But the thing is that hydrogen is not the only thing that is escaping. So the atmospheric escape is so intense that there is also a drag of metals. And that's why we really don't have a huge enhance in the metallicity, because it's not only hydrogen escaping, it's the metals as well. And what you can see here is the evolution of the spectral features with time. And the different colors are showing some molecules that we were particularly interested in, which are SO2, CO2, and methane. Methane, because we didn't observe methane in this planet and we wanted to know why. And interestingly, we do find methane in a very young WST39b, but as soon as the metallicity increases, we cannot see methane anymore, because basically there is less hydrogen available. And carbon prefers to form CO and CO2 instead of methane. So it's more a chemical thing. But also we try to see what happened with SO2, and we don't see the SO2 features in these simulations, but this is because the metallicity that we obtain at the end is not really the metallicity that we know WST39b has today. It's way less. And because you need a very high metallicity to actually have enough SO2 to show it in the spectrum, this is also reflected in these results. So basically what we are saying here is that the planet had to get that metallicity from the beginning, from the formation process itself, because evolution is not able to enrich the planet as much as we see today. So this is encouraging in the sense that, then we can actually learn about the formation of the planets, looking at the planets today, because it would be way more complicated if we also need to include the evolution with time. Another thing that we did was to see which is the initial metallicity that we need the planets to have in order to observe the features that we see today. And you see that we need to start with very high metallicities in order to find this SO2 bump that we are seeing here. So, really, the planet acquired basically the metallicity that we see today from the beginning. And this is, I think, the result of this paper. Okay, let me finish here because I promised I was going to be around 40 minutes. So here are my take-home messages. First is that I'm very positive that we will be able to learn a lot about the interiors of exoplanets with all the great data that we are getting. So stay tuned. And also about the atmospheres and the evolution of planets. We only did this study for WST-39b, but of course, the atmospheric escape is not always the same. It depends on the planet, it depends on the star, it depends on the semi-major axis between the two. So we are also trying to make this result general to try to understand if this is the case, for which planets this is the case, for which planets we really need to worry about the evolution of the metallicity, and for which ones we can assume, we can make a good assumption saying that it comes from the formation, because of course this will be important to see if we can interpret the spectra that we see today in terms of the formation of the planet or not. So here are the collaborators, especially highlight the work of Amy Luca, my PhD student, and Sanne Blot, my former master student, but of course there were also many other collaborators in this, and thank you for your attention.
Thank you so much, Yamila. That was a great talk. Just as a reminder, you can post your questions in the chat or raise your hand. I have a few questions, but I guess I'll start with the one which is already in the chat from Avi. I think it was the slide just before your first slide of take-home messages, and he's asking about a high point on the right of the plot. So I don't know if you can find this
one
again.
or
no, the population plot of all your models against Jupiter and Saturn. That one, yep, right there. So first of all, oops, this is a really cool result, especially the fact that you were closely able to match Jupiter and Saturn, and in general see this really nice relationships. My first question was that one on the far right where you maybe see an upturn above 1.75 or 2 Jupiter masses. Is that real or another unusual case? Maybe that, I don't know, did you guys look at that?
Yes, that's a good question. So some of the planets were very inflated, and especially this one that I see has a high mass, maybe it was also the case. And this method cannot work very well with inflated planets. So we made a first test to see which were inflated and which one were not. And all of them are inflated, of course, which were more inflated than others. But the thing is that when you have this inflation of the radius, then what happens is that you are injecting some energy in the interior of the planet. And for this method, it means adding an extra parameter that we need to retrieve. And that was not working very well with the data that we had so far. So here we just took all of those out, and I'm suspecting that maybe that is one of those. So I have to double check, but great eye.
It could be interesting, right? One way or the other. So, but and my second, I was actually about to type in one in about WST-39b, which is, of course, that you have a much better constraint now for that planet compared to all of these. Where does that fit in this plot? Like, where would that go?
Yeah, it is there actually. So we use WST-39b because there were some data before taken with Haviland Spitzer. So we had some information on the metallicity, so we use it here. But I don't know now which one it is in this plot. But definitely, Yeah,
it was interesting because, of course, your error bars are so large because it's just a heuristic. But now you have a second planet where the error bars are way, 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 way smaller. And it would be interesting if it deviates significantly from Saturn on this plot, or does not.
Yeah, absolutely. So I haven't done the calculations yet with the new
Yeah.
metallicity measurement. So definitely that is in my to-do list. Yeah.
Sounds good. Looking forward to it. Great talk.
Thank you. Prabha, do you want to ask your question?
Sure. Great talk, Yamila, and really interesting work. I guess you kind of answered one of the questions about the model handling inflated planets, because I was wondering about how well it can handle younger planets. So DHR 8799 planets, a bunch of other ones. Are you guys working towards that?
Yes. So we didn't include that in the calculations that I showed, but now we are adding that as well, because of course for exoplanets, right? They are inflated, so we need to deal with that as well. So we are working towards that. Yeah.
Gotcha. And the other thing that I wanted to quickly ask, and it's a little wilder, and this kind of touches on WASP 39b, especially with this inhomogeneous kind of model, which seems to be more realistic. You probably have scattering. You probably have planets that have been bouncing around during formation. What happens when you get a rocky metal thing that flies into a big gaseous one? How does it affect inhomogeneity? How does that influence metallicity?
So there are some papers done about that, but for Jupiter. And because basically when we found out that we needed this elute core to explain the data, we just didn't know how to form this elute core in the first place, because all the formation models at the time just assumed that, the core formed first and then you accreted the gas. So there were some studies on giant impacts, and actually at least one paper that I know, they are able to form these in homogeneous interiors with giant impacts. So it could definitely help. But of course, with these kind of simulations, you need to have the proper target, the proper direction. So I don't really know in a general way, but I think that it actually helps to mix things up in your planet.
Very cool.
But I don't know in exoplanets really. I haven't seen any paper on that yet.
Somebody needs to write that. Thanks, Yamila.
And then there's a question in the chat from Dana, who asks if you plan at some point to do any theoretical work on sub-Neptune. So if you want to focus at some point on planets that are not found in our solar system.
Yes, definitely. I think the smaller planets are very interesting. Although the smaller the planet, the more complex it is. So if you go to smaller, it means more metals and less hydrogen, and that complicates things. But I think that's something that I want to study in the future. So one of my students is actually going to be starting working on that soon, is to understand what happens when you extract, a huge amount of mass from your planet. What happens with the structure? How do things change? How does the pressure and temperature profile behave? Do you have new immiscibility or different layers in the interior forming? So I think that these small planets that maybe lost a lot of their mass due to escape are very interesting to understand from the theoretical point of view. So, but I haven't done work on this yet. It's just in the planning.
Great, thank you. And then Jessica asks, is your work able to estimate things like the core volume and thus core mass fraction on exoplanets?
Oh, let me think. So the problem, okay. So the thing is that for the core itself, we are using a relation that was actually derived. So it's a semi-analytical calculation. We are not really using a true equation of state for the core itself. So, so I'm pretty sure that we can say something about the radius, but it's based on that calculation. So, so another thing that I'm doing now is improving the core treatment in Jupiter, and that will then be reflected in exoplanets. So, and that will be more realistic. So I definitely think I can say something about that right now with the mass itself, just using that relation. Yeah, but I don't have the data information right now.
Okay, great. She said very cool. Any other question in the chat or online? I guess I'll ask one of my more ignorant questions. So I'm familiar with interior modeling and very specific retrievals, but why are you focusing on water for like as a characterization for metallicity? Why not another species? Is it because it's like the most readily detectable molecule?
It was mostly because it was the molecule that was observing so many planets. So we have lots of planets with water measurements, but also water is one of the most abundant molecules in the protoplanetary disk. So it's always a good starting point when you are thinking on the metallicity or the amount of metals that you expect the planet to have. But of course, that also depends on where your planet is born. So it can be done better using other elements as well. So I think we use water because it was the best one that we have for many planets. But I'm really looking forward to have better determinations of metallicities now that we can observe more than one molecule, actually.
Okay, yeah, this is interesting. Okay, great. Any more questions from our audience? No? Okay, well, I think we can end a couple minutes early. Yamila, thank you so much again for coming. If anybody has any more questions, feel free to email me or email Yamila directly. And thank you everybody for coming. The next seminar is next Thursday at the same time, and you will all receive an email.
Great, thank you everyone. Thank you. Bye-bye.
Thanks a lot, Yamila. Bye.
Thank you. Bye.